Every AI you've ever chatted with is built on the same fundamental mechanism. It's called autoregressive next token prediction. Here's how it works. You give the model a sequence of words, tokens, technically. The model looks at everything so far and asks, what's the most likely next token? It picks one, appends it to the sequence, and does it again. And again. There's no master plan. The model isn't trying to make a point or convince you of something. It's optimizing for one thing only, a plausible continuation of the text it's seen so far. That's the entire goal. Every single token requires a full pass through 80 or more layers of neural network. For a 1,000-word response, that's 1,000 forward passes. And the model never checks its work. Each token is final the moment it's generated. So what does that forward pass actually look like? Let's walk through what happens inside for a single token. First, tokenization. Your sentence gets chopped into subword pieces, thinking might become think and ing. Each piece maps to a number. That number goes through an embedding lookup, a giant table that converts each token into a dense vector, a list of thousands of numbers that captures its meaning in mathematical space. Then the real work begins. The vector passes through a stack of transformer blocks. Each block does two things. First, self-attention, every token looks at every token before it and decides what's relevant. Then a feed-forward network transforms that attention into new representations. At the end, the model produces logits raw scores for every word in its vocabulary. Softmax turns those scores into probabilities. And a sampling strategy, top K, top P, temperature, picks the actual next word. All of this, for every single token. In about 50 milliseconds. Now we hit the central question. When an AI solves a math problem or writes a line of code, is that reasoning? Or is it just really, really good pattern matching? The case for pattern matching is strong. Change a few numbers in a math problem, swap John has 5 apples to Maria has 8 oranges, and accuracy drops. Not because the logic is harder, but because the surface pattern shifted. Models are famously brittle to irrelevant context. Add a paragraph of nonsense before a logic puzzle, and performance tanks. But here's the other side. Models can solve genuinely novel problems, math competition questions they've never seen before. Chain of thought prompting dramatically improves their performance, which suggests they're doing real intermediate computation. And mechanistic interpretability research has found actual algorithmic circuits inside models, genuine logic gates that compute modular addition. The honest answer? It's both. Models exhibit what I'd call behavioral reasoning. They can produce correct reasoning chains, but they don't necessarily have a causal model of the world driving those chains. They simulate reasoning using patterns that happen to correlate with actual reasoning. There's a famous framework from psychologist Daniel Kahneman that helps make sense of this. He divides human thinking into 2 systems. System 1 is fast, automatic, intuitive. Recognizing a friend's face. Knowing that 2 plus 2 is 4. It happens instantly, without effort. System 2 is slow, deliberate, analytical. Solving a calculus problem. Planning a vacation itinerary. It takes time and mental energy. Now here's the key insight. Standard LLM inference is pure System 1. One forward pass. No deliberation. The first computation is the only computation. The model doesn't stop to think, it just produces. Chain of thought is a clever trick that simulates System 2. By prompting the model to output intermediate steps, you're forcing it to generate tokens that act as scratchpad memory. Those tokens extend the model's effective computation, giving it space to store intermediate results, check assumptions, and correct course. But it's a simulation. The model architecture doesn't have a built-in System 2. It's still just predicting the next token, over and over, it's just that now those tokens happen to look like reasoning steps. In 2022, a group of Google researchers published a paper with a remarkably simple finding. Add the phrase "let's think step by step" to your prompt. That's it. Just 5 words. The results were staggering. On grade school math problems, performance more than doubled. Overnight, chain of thought became the standard technique for getting LLMs to reason. Here's what makes it fascinating. COT is an emergent ability. Small models show almost no benefit. But somewhere around 100 billion parameters, right around the 70 to 100 billion mark, the ability suddenly appears. The model learns to use its own output as working memory. Since then, researchers have pushed the idea further. Self-consistency, run COT multiple times and take a majority vote. Tree of thought, branch into multiple reasoning paths and explore them. Graph of thought, even more sophisticated search over reasoning structures. The core insight? These models can think, if you force them to. But they won't do it on their own. In late 2024, everything shifted. OpenAI released o1, a model that doesn't just simulate reasoning. It actually reasons internally. Here's how it works. During training, o1 was trained with reinforcement learning not just to produce the right answer, but to produce effective reasoning traces. It learned to generate internal chains of thought, verify its own steps, backtrack when it hit dead ends. The result is a model that can think 4 seconds or even minutes on hard problems. And crucially, the more inference compute you give it, the better it performs. This is the first real inference time scaling law. You can trade more computation for better answers. Then DeepSeek R1 proved this wasn't unique to OpenAI. Their open-weight model showed that reasoning behaviors emerge from pure reinforcement learning, no human-written reasoning examples needed. The model taught itself to think harder on difficult problems, to verify its answers, to backtrack. This changes the debate. Standard models simulate reasoning via pattern matching. These models actually allocate computation, explore paths, and self-verify. It's closer to what we'd call thinking. But let's pump the brakes. Because there's a powerful philosophical argument that none of this is thinking at all. In 2021, researchers Bender and Gebru coined a devastating metaphor. LLMs are stochastic parrots. They probabilistically mimic human language without understanding, just as a parrot mimics speech without comprehension. They reproduce patterns from training data. They don't know what those patterns mean. This echoes a much older argument. In 1980, philosopher John Searle proposed the Chinese room. Imagine a person in a room with a rulebook for manipulating Chinese symbols. Someone passes in characters. The person consults the rulebook, follows the instructions, and passes out the correct response. To the outside world, the room appears to understand Chinese. But the person inside doesn't understand a word. The mapping to LLMs is uncanny. The transformer is the person. The weights are the rulebook. Input tokens are the characters. And the model doesn't understand meaning, it just manipulates symbols. The rebuttals are worth hearing. The system's reply says the room as a whole person plus rulebook understands, even if no single component does. And Searle's argument targets symbolic AI, not subsymbolic neural networks with distributed representations. But the tension remains. And it's exactly that unresolved tension that makes this question so fascinating. Let's look at the hard limits, the things models genuinely cannot do, and may never be able to do. The symbol grounding problem. Models know facts about the color red, but they've never seen it. They can describe the taste of chocolate, but they can't taste. They discuss pain without experiencing it. All their knowledge is secondhand, abstracted from text, not grounded in the physical world. Causal reasoning is fundamentally absent. Models learn correlations, not causal structures. Ask them what if this had been different, and they struggle. Counterfactual reasoning requires a causal model of the world, and LLMs don't have one. Self-awareness is simulated, not genuine. A model can say as an AI, I don't have feelings, but it's pattern completion, not introspection. Models have no persistent identity, no awareness of their own limitations, no intentional states. These aren't temporary bugs. They may be inherent to the architecture. Language models don't think the way we do, they approximate thought through statistical correlation. And approximation has limits. After all of this, the transformer blocks, the attention mechanisms, the chain of thought tricks, the reasoning models, the philosophical critiques, we come back to the same question. Does AI actually think? The honest answer is, it depends on what you mean by think. If thinking means having a conscious, self-aware, intentional mind, then absolutely not. No AI today qualifies. The Chinese room argument has genuine force. Models don't understand meaning the way we do. But if thinking means something broader, the capacity to take in information, process it through multiple stages, allocate computational resources, explore possible solutions, and arrive at correct answers, then something is happening. Something real. Something that was not present in any machine before 2022. I think the most honest framing is a spectrum. AI thinking isn't binary, it's not just pattern matching or genuine reasoning. It's something new. An alien form of cognition, built on architectures that don't resemble the human brain at all, but that produce outputs that increasingly overlap with human reasoning. And that's what makes this moment so incredible. We're not trying to replicate human thinking. We're discovering a new kind of thinking and trying to figure out what it means. So, does AI think? I'm genuinely curious what you think. Drop a comment. Are these models having genuine thoughts, or are they the most sophisticated impressionists we've ever built? Subscribe for more deep dives into the philosophy and engineering of AI.